Let's look at the next function transformation. This is a fun one where we are looking at adding a constant to the function. For this example from x squared, our base function, we are saying think of what happens when we take the x squared and then add 1. So order of operations is still find the x squared first, get your result. It'll be exactly what you would see here, but then add 1. So we can plug in these x values and get these results, and then we can see that each of these function values has been increased by 1. Even the point at the origin has now been increased by 1. We will see it at the point 0, 1. And definitely if we went one by one and plugged these values in place of x, we'll get the same results. If x is 1, 1 squared is still 1, and then add 1 to make it 2. Bump it up to 2. So what will we see on the graph? Here's the base function, and if all of the function values have just been bumped up by 1, our graph has just been shifted upward. Now don't confuse this with the stretch where we saw the points on the x-axis did not move because we were stretching away from that x-axis, stretching up, stretching down, pulling it away from the x-axis. But now the entire graph has actually been moved, shifted up 1 unit. What used to be at 1, 1 is now at 1, 2. And what used to be at 2, 4 is now at 2, 5. Everything just moved up 1 unit. And it's pretty clear for us to see why. We found our x squared and then added 1. And since the function value is the same as the y coordinate, every point has been bumped up 1 unit. Let's look at the other base function. We take 1 over x, get the result, and then add 1. So to the negative 1/2, we add 1 and get positive 1/2. And so on down the line, undefined. As soon as we put the 0 in place of x and get an expression that's undefined, a fraction with 0 in the denominator, it ends there, and we simply have an undefined result. So there will be no graph when x equals 0. We'll see the vertical asymptote. And when x equals 1, we get 1 over 1 is 1, then the plus 1 equals 2. So every function value has just been increased by 1. And we'll expect to see from our base function a shift up of 1 unit. So from 1, 1 shifted up to 1, 2. From 2, 1/2 is now up to 1.5. From 1/3 is at 1 1/3. Every point just shifted up 1. And even where we had negative function values, since this is just add 1, it means shift it up 1. It's not going away from the x-axis because it's not being multiplied. We're not making it more negative. We're saying you got to take your value and increase it by 1. So let's summarize this. We're going to represent this transformation as our function and then a number added to it. We'll call the number d. We're adding a constant to the function. After you get the function value, add a number to it, and it will shift the entire graph up when we're dealing with a positive number. I think you expect what's going to happen when we look at negative numbers. Let's go with x squared minus 2. So our function values have now been decreased by 2. Negative 2 squared is still 4, but then take away 2, it's bumped down to 2. And the rest of these are all 2 less than their original value of f of x equals x squared. Let's look at the graph of this function. The base function f of x equals x squared, and when x squared minus 2 is graphed, all the points have been shifted down 2 units. From 2, 4 down to 2, 2. From the origin down to 0, negative 2. Every point shifted down. And we can see from the expression here, we're taking x squared and then subtracting 2. Every vertical coordinate is shifted down 2 units. Let's also look at the reciprocal function, 1 over x minus 2. Each of these function values decreased by 2, from negative 1 down to negative 3. Undefined, we cannot add or subtract to that. 1, take away 2, down, and so on. So we'll look at the graph, and we definitely see the points like 1, negative 1, 2, negative 1.5. Every point shifted down 2 units. So we can summarize this by saying if d is negative, we're going to be shifting the graph down. Shift up when it's positive, shift down when it's negative. Definitely it's a direct result from what we see here. You got your function, take away 2, basically means whatever you had for x squared, bring it down 2. And if it's adding, then we're bringing it up. So we've looked at 2 transformations so far. Both of these transformations were numbers that were applied to the function, to the result of the function. When we think of graphs of the function, we think of the function value being the same as the y-coordinate. So a transformation like this d transformation, that is a constant being added to the function, means that we're adding something to the result of the function. We're adding to its y-coordinate. This will move the coordinate up, shift it up some number of units, or shift it down some number of units, some kind of vertical change. And when we multiplied the function by a constant a, that a transformation, again it was a vertical change because we were affecting the result of the function, what happened after we plugged in our variable x. So since we're changing the value of the function, we're changing the y-coordinate, the vertical coordinate. And if we're multiplying, we're actually saying multiply this constant to each of the points. If our function value is 2, then multiply it by that constant. If it's 3, make it 3 times as large. If it's 1/2, make it half of its size. Some sort of vertical stretch or compress. So these things that we do to a function is altering the graph vertically. We're changing the function value, which is the vertical coordinate, so we're making some kind of vertical change to the graph. The next two transformations that we'll look at will be pertaining to not the function as a whole after we evaluate it, but actually to the variable inside the function before we even try to evaluate the function. And these have some very interesting results. We'll get to those next.